In this chapter, you will learn about integration of function of complex variable. Before that, let us see differentiation and integration of a complex valued function of real variable. Say Wt equal to ut plus iota vt. Complex valued function of a real variable t, Wt. So its differentiation is given by w prime t equal to u prime t plus iota v prime t. Differentiate the real part and imaginary part with respect to t. Okay. Following this definition, the usual rules of addition of differentiation of two functions, multiplication, etc. The usual rules are followed, but this definition doesn't respect the mean value theorem of differential calculus in reals. Do you know the mean value theorem, in particular the Rolle's theorem? Recall the Rolle's theorem for a function of real variable. If fx is continuous on closed interval ab, differentiable on open interval ab, and fa equal to fb. Continuous on closed interval ab, differentiable on open interval ab, and fa equal to fb, then there exists some c in the open interval ab such that f prime c equal to 0. This is the result of Rolle's theorem. You know it already. This theorem is not respected here with this definition. See this example. Consider the function Wt equal to e power iota t, and t belongs to the interval 0 to 2 pi. Now clearly Wt is continuous on the closed interval 0 to 2 pi. What is it? It is cos t plus iota sin t. So cos t sin t are continuous functions on this interval, and Wt is also continuous, of course. It is differentiable in the open interval. What is its derivative? Iota e power iota t. This is well defined for each t in this interval. Also W0 at the end points value of W is 0. 0 or 1? It's 1. It's 1 at 0 as well as it's 1 at 0 and 2 pi. Okay. So all the three conditions of Rolle's theorem are satisfied, but you can see that magnitude of W prime t for all t is 1, which is non-zero always. Means you cannot find any c in this open interval 0 to 2 pi for which W prime t is 0. So the mean value theorem is not respected. Same way we define integration of this complex valued function of real variable in this manner. Wt equal to Wt integral equal to integral of ut plus iota integral of vt. So usual rules of integration are followed with this definition for Wt, but mean value theorem of integral calculus is not respected. That holds true in reals. Do you recall mean value theorem? Fx is continuous in the interval AB. Then integral of fx from a to b is given by b minus a into fc. There exists some c in the open interval AB such that this integral equal to b minus a into fc. So again you can consider the same function wt equal to e power iota t. It is continuous in the interval 0 to 2 pi, but integral of e power iota t in this interval is given by iota e power, not iota, e power iota t divided by iota 0 to 2 pi. What is the answer? E power iota 2 pi minus e power iota into 0. Both cases 1, so you get 0. So this is the value of the integral. Is it equal to 2 pi minus 0 into fc? Fc means here wc for any c in this interval 0 to 2 pi. No. Why? Because wt is never 0. You can check its modulus. Its modulus is 1, which is non-zero for all t. So you cannot find any c for which it is 0. It means it is non-zero, so it cannot be equal to 0. So again you see the mean value theorem of integral calculus is not respected with this definition, but anyways these are the definitions of differentiation and integration for a complex valued function of real variable. Next, there are some definitions. Simple arc. What is simple arc? If zt equal to xt plus iota yt is a continuous function in the interval a to b, then geometrically it represents a curve in the xy plane from za to zb. This is an arc, of course. If it does not intersect itself, the arc does not intersect itself, it is simple arc. What is simple closed curve or simple closed arc? If the curve does not intersect itself except the endpoints, see this example, e power iota t, say t is from 0 to 2 pi, then you know it's a circle. It's a circle. It is a simple closed curve. It does not intersect itself except the endpoints, okay, 0 and 2 pi. So it is simple closed curve. Next, smooth arc. An important definition. What is smooth arc? This arc is said to be smooth in the interval AB if z prime t is continuous in the closed interval AB, differentiable, of course it is differentiable, z prime t is continuous on closed interval AB and non-zero in the open interval AB. With these two conditions, this arc is called smooth arc. Okay, this curve is a smooth curve. Z prime t is continuous on closed interval AB and non-zero on the open interval AB. Then it is smooth arc. Examples you can take: zt equal to t plus iota t. Say t varies from 0 to 2. Do you understand what is it? It's a line segment from origin to 2, 2. Okay, so this is smooth arc. Likewise, this is also smooth arc. This is a circle traversed in counterclockwise direction. If I put minus here, what is it? It is again a circle, but this time it is traversed in clockwise direction. Okay, opposite. Next, a very important definition term, that is contour. What is a contour? Contour is a piecewise smooth arc. Piecewise smooth arc. I'm writing here piecewise smooth arc. Smooth arc I've already explained here. Piecewise smooth arc means contour is an arc consisting of finite number of smooth arcs joined end to end. It is a single smooth arc, it is a contour. It is also a single smooth arc, contour. Now see this shape, triangle. This is also a contour. It carries three smooth parts, this side, and this side. This is a simple closed contour. This is also a simple closed contour. This is also a contour, but it is not simple because it intersects itself. Okay, so you should understand the difference between these terms. So we'll be using simple closed contour again and again. So you should know what is a contour and what is a simple closed contour. Now let us see what is integral along a contour, or you can say contour integrals. Contour integral. Suppose f is a piecewise continuous function on a contour C given by zt plus z equal to xt plus iota yt, xt plus iota yt, where t belongs to the interval ab. Suppose f is piecewise continuous on this contour, then integral of f along C, denoted by this symbol, this is merely a notation, is defined as integral a to b f zt z prime t dt. This is the definition of contour integral along a definition of integral of fz along a contour C. Okay. Existence of this integral is ensured because we are saying that f is piecewise continuous, z prime t by definition is continuous, so overall this integrand is a continuous function, so it exists. Now let us see an example of a contour integral. Solve this contour integral along the contour given by mod z equal to 1. See how we do it. First you should know its parameterization, because you need to substitute zt here in place of z. So what is z here for this circle in terms of t, e power iota t, and t goes from 0 to 2 pi. So 0 to 2 pi, in place of z, we substitute e power iota t. So z bar is e power minus iota t, and z prime t is what from this? Z prime t is iota e power iota t dt. This is cancelled. So you are left with iota integral 0 to 2 pi dt. That means iota into 2 pi. So final answer is 2 pi iota. Okay, so you need to write your contour in parametric form. After that, use this formula for solving the contour integral. This is one way for solving the contour integral. Another method is antiderivative method. Okay, let me clean it first. First, you should know what is antiderivative. Antiderivative definition in complex analysis is same as in reals, because we define differentiation in the same way for complex functions. What is antiderivative? Let f be a continuous function in a domain D. When I say domain, do you recall what is domain? Open connected set. Recall the definition from first chapter. Open connected set is domain. So open means I can consider this kind of shape. This is open connected set, this whole region. Okay, so when I'm saying domain, imagine this kind of shape in your brain. So f is continuous in a domain D. Capital F, a function capital F, is said to be antiderivative of f if f is antiderivative of small f if capital F prime z is small f z for all z in D. Now we have a very important result that helps in solving contour integrals using antiderivative. What is it? If f is a continuous function in a domain D, then the two statements are equivalent. First statement is antiderivative of f exists in D. Okay, and second, if C is any contour, C is any contour inside this domain extending from point z1 to z2, then integral of fz along C is given by fz2 minus fz1. Means for solving the contour integral of fz, you can just use the endpoints as you do in reals. In reals, how you find the integral over an interval? You write antiderivative, after that you put upper limit and lower limit. Correct? So this result can be used in complex also, provided the antiderivative exists. Okay. What if it is a closed path? It is a closed path. Let's say this part is C1, this part is C2. And let's call this whole contour as C. So integral of fz along C can be written as integral of fz along C1 plus integral of fz along C2. This is fb minus fa fz along C2. So from this, what do you get? If I change the orientation of C2, means I consider from this point to this point, naturally it is Z2 to Z1, but suppose I write Z1 to Z2, and as it happens in reals, you can write it minus. Okay, so finally you get 0 because these integrals are same, depend on the endpoints only because antiderivative exists. So integral along a closed path inside D is 0. That is the point. Okay. But focus on this result again. If antiderivative exists, integral is given by fz2 minus fz1, means you can use just the endpoints. You need not to parameterize the path. You need not to write in terms of t as you do in original definition. Okay, these two statements are equivalent. Equivalent means if this holds true, this is true, then this is also true. And you notice one more point, that if antiderivative exists, then integral along a closed path is 0 inside D. Now let us see a problem using the antiderivative. Solve the integral z dz where C is any contour extending from 0 to 1 minus iota. Any contour, I am saying. Any contour means it can have any shape from 0 to 1 minus iota. So antiderivative of this integrand exists or not? What is the antiderivative? Z square over 2, you know. So limit is from 0 to 1 minus iota. Because antiderivative exists, you can use the endpoints for solving this integral. 1 minus iota whole square minus 0 square. So if you simplify, you get iota. Check it. So you can use antiderivative approach provided the antiderivative exists. Otherwise, you have to do by parameterization. Now, a very important theorem that is called Cauchy Theorem. Very, very powerful theorem in complex analysis. It states that if f is analytic and f prime is continuous within and on a simple closed contour C. Within and on a simple closed contour C. Then integral of fz along C is 0. If f is analytic and f prime is continuous within and on a simple closed contour C, then integral of fz along C is 0. This is the result of this theorem. The natural, or you can say conventional, orientation of C is counterclockwise. If you change this opposite, then it gets multiplied by minus. Okay, you should know this, as it happens in reals. Alright, so Cauchy theorem you understood. We will not do its proof. Next is Cauchy-Gaurashith theorem. Cauchy-Gaurashith theorem. Gaurashith proved that this condition is not required. If simply f is analytic within and on the simple closed contour C, then this is fine. Integral of fz along C is 0. Okay, integral of fz along C is 0. Why this is a powerful result? The Cauchy theorem or Cauchy-Gaurashith theorem. See this example. E power z square and C is a closed contour, simple closed contour, anywhere in the complex plane. You can write its answer 0 because this function is analytic everywhere in the complex plane. So its integral along any closed curve, any simple closed contour would be 0 by Cauchy-Gaurashith theorem or Cauchy theorem. Okay, so Cauchy-Gaurashith theorem or simply Cauchy theorem is very helpful in finding contour integrals. So you should note this result. F is analytic within and on a simple closed contour C, then integral of fz along C is 0. Next, simply connected and multiply connected regions. Multiply connected regions or domains. A domain D is said to be simply connected. Say you have a domain here. It is said to be simply connected if you consider any closed curve inside D. Then it carries points of D only. For example, consider this domain. This is a circle. If you consider any closed curve inside this circle, then these points are also the points of this circle, correct? So it is simply connected. Look at this one. This is also a domain with two boundaries, inner circle and outer circle. Inner circle is this one, mod z equal to 1, outer circle mod z equal to 2. Your domain is this thing. This part, these all points belong to the domain, this domain. Now, see this closed curve. This is completely lying inside this domain, but these points are not part of this domain. Okay, so it is multiply connected region. Or in simple words, we can understand a region having more than one boundary. Okay, this kind of ring-shaped region, it is multiply connected. It's not simply connected. So now we have the extension of Cauchy-Gaurashith theorem or simply Cauchy theorem. Extension of Cauchy theorem. Suppose fz is analytic in a simple closed contour C. Okay, let me read it like this. Suppose fz is analytic within and on this multiply connected region. Okay. Then the extension theorem says that integral of fz along C is same as integral of fz along C1. It has a simple proof you can see in the lecture notes. Means integral along C, if you need integral along C, you can do the integral along C1, no problem. This is also called principle of deformation of path. Principle of deformation of path. Why? Because you have deformed the path to a smaller contour. So it's principle of deformation of path. This result extends to more than one contours inside C. Suppose F is analytic. In this region, between the contours C, C1 and C2. Then this result extends like this. Integral of fz along C is given by integral of fz along C1 plus integral of fz along C2. You can consider more contours inside C. So it's a useful result that you should keep in mind. Extension of Cauchy theorem. See how do we use it. Solve this integral along a contour C, where C is any contour that lies inside a circle okay. The statement reads like this: where C is any contour such that a circle of radius less than 2 lies inside C, of radius less than 2, any circle of radius less than 2 lies inside this contour. So let us construct a circle of radius 1. So by the given statement, this lies inside C. Name it C1. So C1 is mod z equal to 1. Okay. Then F is analytic in this ring-shaped region, or say multiply connected region. And by extension theorem or extended Koshi theorem, what can you say? Integral of this integral is same as integral of 1 over z along C1. But C1, you know, it can be parametrized in the form e power iota t, where t is from 0 to 2 pi. So 0 to 2 pi, z is e power iota t, z prime t is iota e power iota t dt. You can simplify it further, you will get 2 pi iota. Okay, so what has been done here? C is not given to you. It is said that it is given in the statement that a circle of radius less than 2 lies inside it. Less than 2, so we can use a circle of radius 1 whose parametric form is very easy to write, and you can simplify this integral in this manner. Okay, so this way you can use principle of deformation of path, because this C could have any arbitrary shape. So principle of deformation of path is very useful. Next is a very powerful result for solving the contour integrals, that is Cauchy integral formula. In shortcut you can call it CI formula. Let us see the statement. If f is analytic within a known A, positively oriented simple closed contour C. Positively oriented means counterclockwise, the conventional one. The word positively oriented is also used for it. So if f is analytic within a known is positively oriented simple closed contour C and Z naught is any point inside C, then fz naught is equal to 1 over 2 pi iota integral of fz over z minus z0 along C. Fz naught can be calculated using this integral. This is Cauchy integral formula. Again see the statement: if fz is analytic within a non-simple closed contour C, positively oriented simple closed contour C, and z naught is any point inside C, then value of f at z naught can be calculated using this integral. Okay, you can see its proof also. Construct a circle around z naught. Name it C1. You see z naught is making a problem here because z equal to z0 is a singularity of this integrand. But if I enclose this z0, where is z0? Z0 is the center of the circle. Then in this region there is no problem. Fz over z minus z0 is analytic in this ring shaped region. So I can use principle of deformation of path. I can write integral of fz along C1. C1 I am choosing a circle of radius r. That means z equal to r e power circle of radius r centered at z0. So I should write mod z minus z naught equal to r. That means z is z0 plus r e power iota t, and t goes from 0 to 2 pi as usual. So I was saying that integral of fz along C can be written, integral of fz over z minus z naught along C can be written equal to integral of fz over z minus z naught along C1 using the principle of deformation of path. Okay, because this function is analytic in this ring shaped region. It is not analytic at z0, but z0 is enclosed inside C1. So it is analytic within and on this ring shaped region. Okay, now because it is parameterized in T, you can simplify it further. 0 to 2 pi f z0 plus r e power iota t, z minus z0 is r e power iota t, z prime t is r e power iota t into iota dt. This is cancelled. Now because the radius of the circle is at our discretion, I can make r as small as we like. So making r approaching to 0 on both sides. On this side there is no r. What do you get? 0 to 2 pi in the limit r going to 0. fz0 into iota dt. Now it is a constant, you can take it outside and apply the limits of integration. You get 2 pi iota fz0. So from this, what is fz0? Divide this 2 pi iota on the left and you see this result. Okay, so proof of Cauchy integral formula is simple, but this result is very powerful. This can be generalized for the derivatives of f at z0 also. We can find nth derivative of f at z0 by using this formula. Here also it becomes n factorial. Okay, so this is Cauchy integral formula for finding nth derivative of f at z0. Fn z0 equal to factorial n over 2 pi iota integral of fz over z minus z0 power n plus 1 along C. Let us see how this integral helps in finding contour integrals. How this formula helps in finding contour integrals. See this example, z cube plus 2z square minus 1 divided by z minus 1 cube. And C is the contour given by mod z equal to 2. Now see whether this matches with this one or not. From this formula you can write integral of fz over z minus z0 power n plus 1 dz equal to 2 pi iota fn z0 over n factorial. Okay, so we need this integral, means we can solve this kind of integrals using this right hand side. So does it match with this one? Yes. What is fz here? Fz is z cube plus 2z square minus 1. And what is z0? Z0 is 1. N is, if we compare with this one, n is 2. So using this formula, this integral should be equal to 2 pi iota f double prime. Z0 means 1. F double prime 1 divided by 2 factorial. Correct? So pi iota into f double prime 1. What is f prime z from here? 3z square plus 4z, and f double prime z 6z plus 4. So at z equal to 1 you get 10. You get 10. Correct? So is it 10 pi iota? Yes, it's 10 pi iota. Okay, but check these calculations carefully from your side. 2 pi iota f double prime 1 over 2 factorial. So f double prime 1 we are finding 10 divided by 2 factorial means 10 pi iota finally. But here notice one thing, that this 1 should lie inside this contour. Is it lying inside? Mod z equal to 2. 1 is lying inside, of course, so you are able to apply Cauchy integral formula. What if the contour is given by mod z equal to half? Radius of the circle is 1 by 2. In that case, 1 lies outside. So can you apply Cauchy integral formula? There is no need to apply, because in that case, this whole integral is analytic within and on this contour C. Singularity is lying outside. So you can apply directly Cauchy theorem. According to Cauchy theorem, its answer should be 0, because if a function is analytic within and on the given contour, then integral along such a contour is 0. Okay, So make sure that singularity lies inside the contour before applying Cauchy integral formula. Is it fine? Okay. See another problem. Find this integral along C where C is given by mod z equal to 3. Now this function has two singularities, 1 and 4. And for applying Cauchy integral formula, you need the function in this format. It is not in this format. It should be z minus z naught whole power n plus 1. But before applying Cauchy integral formula, you need to check whether this z0 lies inside the given contour or not. And secondly, your integrand should be in this format. Okay. So here the function has two singularities. First is 1, second is 4. And given contour is a circle of radius 3. 1 lies inside this, 4 lies outside. So how to solve this problem? I can rewrite the integrand in this form. Isn't it? This function is analytic within and on the given contour, and 1 lies inside this. So you can apply Cauchy integral formula now easily. 2 pi iota. Here what is n? N is 0. So no derivative, simply f at 1. You can calculate what is f at 1 here. F at 1 is minus 1. 3 over minus 3 minus 1. Yes, so finally minus 2 pi iota. Okay. So you need to practice problems of different type based on Cauchy integral formula. You will feel comfortable. It's not difficult. Okay. So you can solve contour integrals using Cauchy integral formula if you are able to put your integral in this format. So now you have seen three approaches. First approach, by definition, you parameterize your contour equation and then solve the integral just like a real integral with the limits of t. Second approach, if you are able to find the antiderivative, then you can use the endpoints of the contour for writing the integral, the answer of the integral. And third, this Cauchy integral formula approach. But in this case, what do you need to do? You need to put your integral in a particular format, and secondly, the singularity should be inside the contour. If there is no singularity inside the simple closed contour, then its answer is 0 by Cauchy theorem. So you are seeing different things now for solving the the contour integrals. Now Cauchy integral formula has further implications, very good results based on Cauchy integral formula. First one is, if fz is analytic at some point z0. Hope you recall the definition of analytic function at a point. What is the meaning of analyticity at the point z0? There exists a neighborhood of z0 in which the function is differentiable. If the function is differentiable at every point in some neighborhood of z0, then the function is analytic at z0. So I was telling you the further implications of Cauchy integral formula. If fz is analytic at z0, then all derivatives of fz are also analytic at z0. If a function is analytic at z0, then all its derivatives are also analytic at z0. This can be proved very easily using Cauchy integral formula. Because if fz is analytic, let's do it for f prime z. That can be extended for any order derivative. If fz is analytic at z0, then it is analytic in some neighborhood of z0 like this. Now, inside this, draw a circle, say of radius epsilon over 2. Now, within and on this circle, the function is analytic. So, what does it mean? Using Cauchy integral formula, you can find f prime z0, and in fact, f prime z0 z at any point inside this means the function is f prime is differentiable at every point inside this circle, mod z minus z0 equal to epsilon by 2. If f prime is differentiable at every point inside this, it means f prime is analytic at z0. So this, applying these arguments, you can easily show that if fz is analytic at z0, then derivatives of all orders of fz are also analytic at z0. Okay. In reals, the story is different. Where you talk about differentiability, see this function fx equal to x power 3 by 2. What is its first derivative? 3 over 2 x power half. Second derivative 3 over 4 x power minus half. You can see that f prime 0 is 0. First derivative at 0 exists, but second derivative doesn't exist. It's not defined. Correct? Not defined. So what does it mean? This result doesn't hold in case of reals. If fz is analytic at z0, that means f prime z is ux plus iter vx. You know this result already. So first order partial derivatives of u and v exist. Because f double prime z also exists, you can further differentiate it to get this one. Likewise, derivatives with respect to y also you can write. So what I'm trying to tell that if fz is analytic at z0, then partial derivatives of all orders of its real and imaginary part functions also exist. Next is Morira theorem. What is Morira's theorem? It is converse of Koshi theorem. You can say its statement reads: if a function f is continuous in a domain D and a function is continuous in some domain D, an integral of fz along every closed contour is 0, then f is analytic throughout D. F is analytic throughout D. By the way, if f is analytic, see this result also. If f is analytic in a domain D, then along any closed curve inside D, integral is 0. Why? Because the function is analytic within and on C. So by Cauchy theorem you can say this. Now you are saying reverse. If f is continuous in D and along every closed contour inside D, integral of fz is 0. Now you are saying that f is analytic. Okay. Next we have a theorem called Willis Theorem. This is also a very nice theorem. Willis theorem. It says that every entire and bounded function is constant. Entire and bounded function is constant. You know what is entire function? A function which is differentiable at every point in the complex plane, or you can say it is analytic at every point in the complex plane. Such a function is entire function. Bounded, you know, mod fz is less than equal to m. There exists some real number capital M such that mod fz is less than equal to m for all z. Then such a function is bounded. So every entire and bounded function is always constant. So say fz is entire and bounded. If we show that for any point z0 in the complex plane, f prime z0 is 0, then naturally f is constant. So you can easily prove this result using the Cauchy integral formula. By Cauchy integral formula, what is it? 1 over 2 pi iota integral of fz over z minus z0 whole square dz. Now mod f prime z0 is what? You need to choose a contour. So let's choose a circle around C, around z0 of radius capital R. Okay, so within and on this contour the function is analytic because you are saying it is entire. So whatever contour I choose in the complex plane, it is analytic within and on that contour. Secondly, you are saying it is bounded. So when I take modulus on both sides, what do I get? I get something like this. But if I simplify it further, writing in terms of t, then I will get an expression like this, m over r square, because on C this is equal to r, and further you will see that when you write it in terms of t, you get the length of this contour, that is 2 pi r. So overall, this mod f prime z0 is less than equal to m over r. R is at our discretion. I could choose r very large. If r goes to infinity, this goes to 0. So this shows that f prime z0 is 0. So I chose an arbitrary point z0 in the complex plane and showed that its derivative at this point is 0. It means fz is constant. Okay. Using Liovli theorem, you can easily tell that sin z is bounded or not. Sin z is not bounded, you already know when we discussed chapter 2. There you learned that sin z, in case of real, sin x is a bounded function because mod sin x is less than or equal to 1 for all x. But in case of complex, sin z is not bounded. You can prove this using Liovli theorem. Why? If you say that sin z is bounded, sin z is already entire, so it should be constant, but it is not a constant. So using this reverse argument in Liovli's theorem, you can say that sin z is unbounded. So you see there are various results which follow after this Cauchy integral formula. Likewise, you can prove fundamental theorem of algebra. Any polynomial of degree n has exactly n zeros, real or complex. Any polynomial of degree n has exactly n zeros in the complex plane. There is another useful property in analytic functions. See, that appears in this maximum modulus principle. I will just state this, you will understand. Suppose a function f is continuous in a closed and bounded region. Closed and bounded region. Or suppose f is continuous within a non-closed and bounded region, or and f is analytic and non-constant. Then mod fz attains its maximum value on the boundary of this region, somewhere on the boundary, not inside the region. Let's say boundary is C. Again I repeat, f is continuous on C, f is analytic and non-constant inside C, then mod fz, maximum value of mod fz doesn't lie, means doesn't appear at any point inside C, rather on the boundary of C. If f is analytic, non-constant under the same conditions and non-zero also. Non-zero also suppose, then 1 over mod fz attains its minimum value on the boundary of C but not inside C. This is called minimum modulus principle. Okay. So this is a very useful property of analytic functions. In fact, not only mod fz, the real and imaginary parts of this function also get their maximum minimum values on the boundary of C under these conditions, of course. What is the real part? U plus iota v. So I can write a function like this. E power fz is what? E power u plus iota v. But if I take modulus, what do I get? E power u only. Okay. So if fz is analytic, e power fz is of course analytic. So this attains its maximum value on the boundary of C, not inside C. It means e power u attains its maximum value on the boundary of C. It means u attains its maximum value on the boundary of C. So with these arguments, you can easily prove that real and imaginary parts also follow the same thing. Okay. So with this chapter 4 is over. Hope you enjoyed the concepts of complex integration. Thank you. We will meet in the next lecture.